Monday the 29th of September. So the first thing is we need to write out the formula for these. What did you get for this one? NaHSO4. NaHSO4 plus KH2PO4. Even if you get no reaction, like he mentioned, I still want to see the products, the potential products of this. So what would the products be?
NaH2PO4.
Yeah, NaH2PO4 and KHSO4. Good. All right, then, do we have a precipitate? No, are we going from stronger acid to weaker acid?
No.
No. Do we have gas formation?
No.
And so we have no driving force. If there's no driving force, then what I mean by putting another arrow here, we put another arrow here to say no reaction, right? Because this happens in a lot of these when you, and this is a complete, you get the CE. If we write out the IE for this, what would we get? We get Na plus, do we get H plus SO4 2 minus?
No.
No.
HSO4 minus.
Right, the HSO4 minus ion doesn't break apart or ionize into H plus and SO4 2 minus. Why? Oh, because it's a weak acid, right. HSO4 being a weak acid, it stays together like this. Over here, we're going to get potassium ions. Should I split apart this? So, for example, potassium, 2 H pluses, and a phosphate.
No.
No. This should be written K plus plus.
H2PO4.
Yeah. H2PO4 minus, because the hydrogens stay on. Because it's not a strong acid. Only how many strong acids do you have in ours? 7 strong acids will ionize. All the other acids, these are called acid anions. Acid anions are typically weak acids. So, although if we did this and then we ionize these, then you see there's nothing changed. All the ions would cancel each other out, and so nothing changed. And so we had no reaction when we had this ion mixture.
So what does it mean when we have the complete formula up above and then we show that there was like a double replacement, but
what we do is we analyze these products. So we show these products because you're showing what forms, what could potentially form, and that this isn't going to drive it because there's no precipitate, no gas, and no stronger acid or weaker acid because nothing changed. Actually, what we have here in this particular reaction is we have a beaker with a mixture of ions staying a beaker with a mixture of ions, because when you look at this side, it looks exactly the same. Sodium ions and dihydrogen phosphate, right? And potassium ions and hydrogen sulfate ions. And so we start off with a beaker of 4 ions floating around there, and we end up with a beaker of exact same thing, 4 ions floating around there. Nothing happened. None of the ions combined. Even though we're showing it combining here, they don't combine because they aren't forming anything, i.e. PBT, weaker acid, gas. So nothing changed. Nothing changed, there's no reaction, right? No reaction. But this is wrong. There is actually a reaction here. A reaction does take place. And so I need to change this. I should say no reaction for metathesis, which are ion combinations, and no good ion combination. And so if there's no reaction for metathesis, how many other potential reactions do we have to look for? 2 more, and those 2 are acid base and redox. Right. And so no reaction for metathesis, but we need to consider acid-base and redox. Okay, after looking at potential acid-base reactions and potential redox reactions, then how many more are left? How many more categories of reactions are left to see? In other words,
Acid-base.
well, acid-base and redox, after we do those, then are there any other types of chemical reactions we should look for? For example, should I look at, after doing acid-base and redox, should I look for single replacement? Should I look for combination? Should I look for precipitation? Should I look for decomposition?
No.
Combustion? No, because these are, yeah, this takes care of all those categories. And so for acid-base, let's take a look at that next. There are two types of acid-base ones that we look for, Bronsted and Lewis. Bronsted we're going to cover now. Lewis we're going to cover later. And so let's go ahead and write down the rules or the steps in analyzing reactions for potential acid-base, Bronsted acid-base. Lewis acid-base has a different set of steps that we consider. But Bronsted are pretty straightforward. So when we analyze things for Bronsted, which are called proton transfer reactions. Proton is H+. The first step is we inventory the solution. I'll tell you what I mean by that. Once we inventory the solution, then we know everything, all the major species that are present. Then we identify or find the strongest acid present. Then we find the strongest base present, and then we react these by transferring a proton, called proton, from the acid to the base. Then 5, we look or determine if driving force is present. So those are the steps in the analysis for that. So for this particular mixture, let's go ahead and do the inventory. Step 1. The inventory, we already have most of it down because there are sodium ions present, there are hydrogen sulfate ions, potassium ions, dihydrogen phosphate, and there's one more. Do you know what it is? Water. And so when we inventory, we need to make sure we include water in that inventory because water is present and in pretty high quantity. Plus it has some special acid-base properties to it as well. Okay. So we have a chart over here that we can use to identify the acids and bases. You know, the relative strength of acids and bases chart over there, up against the wall here. But I'm going to show you the handout forgot to turn this on. Here. But the first thing is, take a look at the chart, and do you see sodium ions? In other words, are sodium ions acidic, proton donors? Do sodium ions have an H plus that they can donate?
Yeah.
They have protons, but those protons are locked away in the nucleus. We're not going to be losing those protons. And so there's no H. And so would we consider sodium an acid? No. Is sodium, that is, are sodium ions good proton acceptors? Bases are proton acceptors. So, what do you say? No. I mean, this really doesn't want an H plus. And what would form? If you tried and add an H plus to sodium ions, what would the product be? Just do it on a piece of paper and see. The person always shuts down the computer for me.
Try to add an H plus to Na.
Yeah, to Na plus.
What would it be?
What would it be?
A fallacy, because they're both pluses.
They're both pluses, so yeah, they want to stay away from each other, but what would it be?
You separate Na and H plus on
No. I mean, somebody might try to put it together to form NaH2 plus. That's what it would be. Does that sound likely?
No.
I mean, what would hold them together?
Nothing.
Nothing. Unlikely. Okay, sodium ions are what we call neutral. And so we'll just say, actually, I had the pen here. Neutral. Neutral in this sense means it doesn't want to donate or can't donate, it can't accept. It's neutral. How about HSO4 minus? It'll accept. Could it donate?
Yeah.
Yeah. HSO4 minus, take a look at the acid chart here, or give me a moment, I'll bring up the other acid chart here. So here at the top we have this strong acid. Dividing the strong acids from the weak acids is hydronium. Hydronium is actually the strongest species, acidic species that can exist in water. And then here we have trichloroacetic acid. That's what this is called. And then we have HSO4 minus. On the chart over here, we have our strong acids here, and then there's hydronium. And we have oxalic acid, sulfurous acid, and HSO4 minus. And so a little different mix of acids there in the two charts. But anyway, HSO4 minus is an acid. It occurs on the acid side of the chart. And then we have the bases. These are the conjugate bases of these acids. And so here, HSO4 minus is here, but when I look at the base side, do you see it here?
Yeah.
And so it occurs as both an acid and a base. Then what do we call something that can either donate a proton, an acid, or accept a proton, a base? If HSO4 minus accepts it, it's H2SO4. If it donates it, it converts to SO4 2 minus. Amphoteric. And so HSO4 minus is an amphoteric species, and amphoteric species act both as an acid or a base, depending on what you react it with. amphoteric.
And this is sulfate?
H-
Oh, age, okay.
HSO4 minus. Okay, how about potassium ions? What would you say about potassium? Potassium ions, neutral. That's right. So we'll write that down. H2PO4 minus.
Amphoteric.
Amphoteric. H2PO4 can either donate, i.e. an acid, or it can accept as a base. And so H2PO4 minus would be expected to occur on both sides of this chart. So let's find it. Here's H2PO4 minus as the acid, proton donor. And then where is it as the base?
It's under sulfate ion.
Okay, here it is. Here. So here and here on both sides of the chart. Amphoteric. Okay, how about water?
This is the base.
Yeah, amphoteric as well. H2O occurs on the acid side here and on the base side here. That's water. And so acid and base. Amphoteric. So we have actually 3 amphoteric species in here. That doesn't mean it acts as both. It's going to act as one, only one. You know, either the acid or the base, depending on what you react it with. But we're not going to have a whole mix of reactions here. You know, what is the most probable reaction? The most probable reaction is picking the strongest of the acids. The strongest of the acids are going to be the one most likely to donate the proton, and the strongest base, which would be the one species that's most likely to accept. And so that's going to be the collision that's going to have the highest probability of reaction. And so out of these 3 acids, which one is strongest?
HSO4 minus.
HSO4. Oh, just one more thing. HSO4 minus is a much better acid than it is a base. It's way better. In fact, you know these bases up here? Like, for example, chloride. Is chloride a very strong base? For example, if you had an upset stomach and you had too much stomach acid, would you take table salt, sodium chloride, to help neutralize that? Because, you know, chloride's a base. No, sodium chloride's not going to do anything. And so these bases here we call too weak to be basic in water. In other words, these are so weak, we call them neutral / quote unquote. We call them neutral as far as basic properties go. Okay, yes, they can accept, therefore we're going to call it a base, but they're so weak, we don't really factor their base strength or basicity into consideration most times. And so that's something about HSO4 minus. Even though it's a very weak base, so weak we don't really consider it, its acid properties are quite strong. You know, it's one of the stronger weak acids here. Okay, so it's heavily biased, but I don't care about the bias. I'm still going to call it an acid base because there is a potential for accepting the proton. Whereas water has equal strength. Its acid strength and its base strength are equivalent. H2PO4 minus, what is it? Is it a better acid or is it a better base?
Better base.
Well, looking at it, here's H2PO4 minus as a base. And the strongest base on that chart is what? On the wall? Amide. What's the strongest base on this chart? It's not amide. The strongest base on this chart is CH3 minus. Do you know what that's called? This is called methide ion. And so as far as the base properties go, H2PO4 minus is a pretty weak base. How about acid? Well, let's take a look. The strongest acid on this chart is, what's that called? Perchloric. And then we go down, H2PO4 minus is way down here, so it's a pretty weak acid. And so it's pretty weak both ways. It's not heavily biased in one direction or other, so in a way it's comparable to water because, you know, either way it's weak, just like water. Water's weak both ways. Whereas HSO4 minus is more biased towards the strong here, at least in the acid. And the base is exceptionally weak. Does that make sense? A little bit? All right, so going through this list of acids, which one's the strongest of the three? We just start off with the strongest perchloric and work our way down, and it turns out we'll hit HSO4 minus first. Okay, now you tell me what the strongest base of the three is.
H2PO4.
H2PO4 minus? See, so let me scroll down here, lock it. Yeah, actually, wait a minute, isn't water?
That's acid.
Water?
That's the acid program.
Somebody said this morning, yeah, water's the strongest, right? But this is not a base, this is water, the acid. And so the way you have to compare it is, you have to compare, you know, apples with other apples, but don't compare apples with oranges, you know? If somebody asks you, what is the biggest apple, then you wouldn't grab the biggest orange and say this, right? And so don't do that. Don't cross it. When we're here, we're going to go up, and the first base we're going to hit is, even though it is weak, it's going to be H2PO4 minus. But water is even weaker, and hydrogen sulfate is so weak, you know, it's pretty much neutral as far as base properties go. And so the strongest base, H2PO4 minus, the strongest acid, HSO4. So even though this is amphoteric, HSO4 minus, when put in the presence of H2PO4 minus, will act as the acid. And H2PO4 minus is amphoteric, but it's going to act as a base in this combination. And so let's go ahead and do the reaction. HSO4 minus plus H2PO4 minus. And so we label this. This is our acid, this is our base. This is going to form what? So we transfer one proton from the acid to the base, which gives us SO4 2 minus and H3PO4. Okay, we did this in one step. As an aside, we could do this in half reactions. And so let's say using half reactions. For example, if HSO4 minus is our acid, then HSO4 minus is the proton donor. It's going to form SO4 2 minus. And so I take this equation off this chart here. Let me flip this over here. Sorry. Video. Over here, HSO4 minus gives a proton and sulfate. And then I'll take this one off the H2PO4 minus, which is on the base side. Where is H2PO4? Here it is. H2PO4 minus will gain a proton to form H3PO4. So I'm going to reverse this reaction here. And so this is what I call the acid part of the half reaction, and then we need our base part of the half reaction. The base part of the half reaction is H2PO4 minus gains the proton to form H3PO4. And then what I do is I combine the two half reactions. When I combine it, the H plus cancels, and so I end up with HSO4 minus plus H2PO4 minus yields SO4 2 minus plus H3PO4. And so here I take care of the proton transfer in steps. All right, now that we figured out what the reaction is, what's left to do?
Figure out which way it's going to be favored.
Which way is favored? That is, we need to see if there is a driving force present. In order to do that, the driving force for acid-base reactions is going from stronger acid-base to weaker acid-base. And so the driving force that we're looking for is stronger acid to weaker acid. And so that means we have to figure out what the acid is on the product side. And so what is the acid on the product side? Yeah, it's got to be H3PO4 because can sulfate donate? No. But sometimes it's hard to tell because sometimes we form amphoteric species here. And we don't know, is the amphoteric species going to act as the acid or the base? Well, it depends on the reaction. Because it can go either way. And so sometimes the easiest thing to do is to reverse the reaction like this. We reverse it and then see who donates the proton, who accepts it. And so if we reverse this, then H3PO4 must be donating the proton because we're losing one. And then HSO4 minus must be accepting. SO4 2 minus must be accepting because we form HSO4 minus, which gave the proton. And so this is the base, this is the acid going backwards. We can also see this in the half reactions. When you look at the half reactions, when we reverse this, do you see that sulfate is picking up a proton going backwards? And so this is our base, and then H3PO4 minus, H3PO4 is losing proton, because that's our acid. So base and acid. Okay, we aren't done yet. We have to figure out which side is stronger, less stable, and which side is weaker, more stable. So the easiest thing to do is just compare the two acids. Which one's a stronger acid, HSO4 minus or H3PO4? HSO4 minus. And so we're going from stronger acid to weaker acid, and therefore we have a driving force. But are you familiar with the conjugate relationship between acids and bases? Yeah. And so let me take a minute and let's talk about the conjugate relationship here. The conjugate relationship goes like this. If we have a strong acids are excellent proton donors. That is, they lose the proton quite easily. If we have a strong acid like this, then is perchlorate, its conjugate base, strong or weak? It's got to be weak. It pretty much has to have minimal attraction for the proton. Because if perchlorate really wanted that proton, it would hold on to it much tighter. And therefore, HClO4 wouldn't be as strong of an acid. So all of these have minimal affinity for a proton, right? Because otherwise they wouldn't be strong acids. They would have a much harder time letting go of that proton. And so strong acid means weak conjugate base. Now for the 7 strong acids means that the conjugate base is so weak, we don't really consider it much of a base. Just think chloride. You aren't going to be neutralizing many acids with chloride. Whereas if we have a very weak acid, like methane, do you think methane really wants to lose that proton? No. But if it does, then we form something called methide. Methide is an extremely powerful base because it really wants a hydrogen atom, a proton back. So a very weak acid like methane means an extremely powerful base like methide. Methane, when we were talking about the chemical properties of hydrocarbons, we said that it's pretty much no metathesis, no acid base, only redox, combustion. And that's pretty much it. Because do you think this is a very good, in fact, most charts leave methane off? Because methane really isn't a good acid. Oh, it's pretty much neutral. And so you aren't going to be neutralizing any bases with methane. These extreme species like methane, the only way you could get that to react as an acid is by using a super base. Something way off the charts, strong, as far as base goes. The base would have to be stronger than methide. So what's a stronger base than methide? It's somewhere down here. Do you know? No. It's not as common. So, anyway. Going back to this, then, so if the acids follow, the bases must follow too. And so it's going to be a stronger base to weaker base. I don't even have to check the chart, but we could check the chart just to verify. H2PO4 minus must be a stronger base than SO4 2 minus because of the conjugate relationship. And so let's take a look. H2PO4 minus here is a stronger base than HSO4 minus. Oh, not HSO4, sorry. SO4 2 minus. So H2PO4 minus is a stronger base than SO4 2 minus. And so it's correct. So the driving force would be stronger, stronger to weaker, weaker. Sometimes people have this. They have strong, weak, strong, weak. That doesn't happen. It's impossible because of the conjugate relationship. So this is our driving force. Therefore, we expect this reaction to occur. This is the same thing here. And so there is actually a reaction. What is the reaction? It's a acid-base reaction. Finally, we check for redox. But we aren't going to do that now. All right, so let's do another example of this. Let's do a manganese to chloride and sodium amide okay, the manganese 2 chloride will be aqueous, the sodium amide will be solid. So I'm going to stop the recording and make it into 2